Welcome back, class. As I said in the last video, we are going to take a look at an enamine reaction and show you the mechanism. So the first step is when we look at our secondary amine, the lone pair on that secondary amine is going to come in and attack the carbonyl carbon. And that first process is reversible. So what are we going to get here? We are going to get a negative charge on that oxygen, and then that nitrogen attacked. So we're going to have that right there, and we still have our hydrogen on there. So what's the formal charge on that nitrogen now? You would see that has a positive charge. And we see that these are under acidic conditions. And recall that this is basic and this is an acid. So when you're going to have a little bit of excess of the amine, and that's going to react with the acid. And so what you're going to have is this species right here, this protonated amine. And so when you have that, that's going to be our proton source. Okay? And so what's going to happen is we're going to protonate the alkoxide. And that will give us that's positively charged, and then our OH. And then that will give us our base back, like that. And if we're drawing in the lone pairs, we would do that. Now then we have one more step here. So this is reversible. And we can see, hey, this nitrogen has a positive charge. So we're going to come in and take this and get rid of that positive charge to give us OH and RR, like that. And then what did we regenerate again? We generated our acid. Hydrogen, hydrogen, and that would be what? Positively charged. Now this molecule right here, this has a name, a very special name, and that's the carbonylamine. Remember talking about that one? Let's write it down just in case. Where do I want to write it here? So this molecule right here, that has a special name, and I'll write it right here. Give myself a, see if I'm spelling this right. Carbonylamine. Did I get it all on the page? And that is that molecule there. Just a special name. So let's erase this first. Like that. Okay. So we're not done yet. That's not our enamine. That's our target, right? So what do we have to, when I pause for a moment, what has to happen? I have to, there's no oxygen atom in the product, so I got to get rid of that. So how can we do that? Well, can a hydroxide just leave? No. But look at what we've got here. We've got an acid. Our lone pair that can come and grab that. And what does that do for us? Well, it converts it into a good leaving group. That's water, right? And R. So now we have a good leaving group, and what else did we have? We generated our base again. We got that back. So water is now going to leave. How's the water going to leave? Well, these lone pairs can come in. Let's use the same color here. So these lone pairs can help kick off the water. And let's see, that's going to come down here. We're running out of board space here. So I have a double bonded nitrogen R. And what was released? Water came off. Okay. No, there's no lone pairs on that guy. That nitrogen has what? 4 bonds. So that has to be positively charged. Now, is that our product? Nope, it's not there yet. What's going on here? So what can we do to get to our product? Well, what do we have right here? You see that this carbon here only has 2 hydrogens, and these have 3 each. So the product is showing us that we have to take off one of those hydrogens. So what if we took the base from this step, grab that proton, take the 2 electrons in that carbon-hydrogen bond, dump it there. Now what am I missing? I've now formed a Texas carbon, so I have to take those electrons and put them there. And lo and behold, if I can draw my arrows right, this is a reversible process. Let's see here. So that gets us to our product. So this right here, we rip off a proton using the base, and then it goes right into our product. See that? Isn't that pretty cool? And to be more consistent here, we could, what proton did we actually take off? There. See that better. So that is the mechanism for the formation of an enamine. Now the reason why we form the enamine is because if this group right here was not a secondary amine, it would have another hydrogen coming off of this species right here, and then this base would have ripped off the hydrogen to form the imine. But because there's no hydrogens on the nitrogen at this intermediate, the base has to rip off a hydrogen from the carbon, giving us the enamine. So I would highly recommend that you compare and contrast the mechanism when you have a primary amine, which forms the imine, and then compare it when you have a secondary amine, which then forms the enamine. And just look at the differences, and I want you to focus in at this part of the game when you compare the two. Okay? So this is what I'm talking about, this particular example. So here we have a ketone, we have a primary amine, we get the imine. But if we take the same ketone but replace one of these hydrogens with the methyl group, and now we have a secondary. What is the product going to be? It's going to be this. And I want you guys to do the mechanism for both of these products and see why these hydrogens right here, these two and this one, where they come into play and why they are so important. The next reaction that we're going to look at is a reduction, and it's called the Wolff-Kishner reduction. Don't want to misspell this. So Wolff with two S and Kishner. Pretty sure Wolff is a German chemist and Kishner is a Russian chemist who discovered this process. And the process is a reduction. And what we're going to do is get rid of the ketone and convert it into an alkane. And this is a two-step process in which you add some acid, and then you're going to use a molecule right here. This molecule right here is called hydrazine. So you use some hydrazine, and as you do the reaction, you're getting rid of water. And you get rid of water based off the apparatus that you're using. And when you do this first part of the reaction, you're going to then form like that. You'll form that species right there. And that resembles an imine. And then you do the second reaction, or the second step. I'm going to try to make a smaller arrow for this guy. You add some potassium hydroxide and some water, and you're going to heat it up. I'll use the delta symbol for heat. And then that is going to pop off this piece right here and give us our product. Like that. That is a Wolff-Kishner reaction. It's done in two steps. The key players are the hydrazine, the base and heat, and then it gives us it goes from a ketone all the way to our alkane. So in the next, or what we're going to go over next, is going to look at the mechanism of how this happens. When I was looking at this product right here, or this intermediate, I called it imine. It looks imine-like. It actually has a different name. So if it was an imine, it would have a alkyl group, so something with a carbon. But you see here, it is a nitrogen species. So this functional group is actually called a hydrazone. Let's see if I spell this right. Hydrazone. So when you have a nitrogen double bonded to some carbons, and then directly attached to it is another nitrogen, it is a hydrazone. Okay. Now, what if you had a species where that R group is a OH, like that? What if you had something like that? That also has a different name, and that is called a oxime. So I just wanted to make sure that you're aware of those two different names. So if you see those, you know what we're talking about, okay? So now it is time to go look at the Wolff-Kishner reaction. So let's look at the Wolff-Kishner reaction. That's where you take a ketone and reduce it down all the way to the alkane. The first reaction is the same mechanism that we've been going over when you form the amine. But remember, this right here is called a hydrazone. So to go from here to here, you're following the same mechanism when you form an imine. So I'm not going to show you that mechanism again because it's exactly the same. But then when you get to the hydrazone, you do the second reaction, which is the basic. Work up and you add some heat. So this is where we're going to start. So I'm going to expand out the hydrogens on this hydrazone because those hydrogens are going to be very important in the reaction. And I lost the top hydrogen, but that will be okay. We'll fix that later. So the base is going to come and rip off one of those hydrogens. I'll draw it a little bit lower here so we can get everything. And that lone pair was already there, and we just tacked on a new one. And we generated some water. Now, what would the formal charge on this nitrogen be? That would have to be a -1 formal charge. But when we take a look at this molecule here, we'll go over here. We're going to see a resonance structure. What can happen here? Let's change the color. Like this. So now we could have a structure and then a lone pair there, so that would be negatively charged, just like that. Now, double checking the formal charges here. Are we all good? Still a lone pair there. Okay, so there's a resonance structure. Now, why is that resonance structure so important? Because now it can show us that this carbon is electron rich. Because if we take a step back and say, hey, this ketone is going to be turned into this alkane. So if we number the carbons, what do you see? How many hydrogens are on carbon 2 here? 0. And then how many are here? There's 2. So we have to add 2 hydrogens to carbon 2. So that's electron rich. So what that's going to do is going to, let's see, yes, it is going to take the lone pair here and grab that and give us and so we added our hydrogen, and I'm not going to draw in the hydrogen, but we now added it. So now it's neutral. Well, what did we just regenerate? We generated our hydroxide right there. Okay, are we to our product yet? Not quite. We need to somehow get rid of this right here. So we've just generated the base, and so that's going to then rip off that hydrogen. So that will be So it would have to be negatively charged, and then we just regenerated some water. And I'm going to actually expand out the water to look like this. Now what's going to happen now is this looks very similar to nitrogen gas. And nitrogen gas is a good leaving group. And so that's exactly what's going to happen here. We're going to have a lone pair come down to form a triple bond. And then this nitrogen carbon bond is going to break, putting the electrons there. Now this step right here is irreversible because we are generating what? We are generating N2 gas. And so in the reaction, the nitrogen gas, excuse me, is just going to bubble away. You can't get it back. It can't come back into the reaction because it bubbles off. And so that leaves us with that carboanion. And so now we just have to do another proton transfer to get us to our product, which is going to be right there. So where's some acidic protons? Right there. And then that is going to give us our product. Pretty slick. So the Wolff-Kishner, very, very important reaction, converting a ketone into an alkane. So I want to remind you that when you are doing a reaction and you're under acidic conditions, your species can be neutral. So like, let's say in your reaction you have water. If you're under acidic conditions, it can be neutral and positive. But it cannot have a negative. You cannot have negative species in an acidic environment because this negative charge right here is basic. And you can't have a basic species in an acidic environment or something with a negative charge. Okay, so that's just a reminder. When you're going through mechanisms, pay attention to your species and their charge states and what kind of conditions are you in. So the next thing that we want to go into a little bit more detail is acetal formation. We've previously went over that and I talked about how it's reversible. So let's just go into a little bit more detail with the reversibility of acetals. So this reaction that we want to talk about now in a little bit more detail is called hydrolysis of acetals. To recall how we do that, well, we have to add lots of water and then a little bit of acid. And when you do that, it's going to hydrolyze those bonds, chop them off, and give us what? Our ketone. Gives us back that ketone. And then the ORs are going to fall off, and that's going to then give us 2 alcohols. So mechanistically, how is that going to happen? But before we get to the mechanism, write this down, put it to memory. It only works under acidic conditions. Does not work or does not work under basic conditions. Doesn't work. It only works under acidic conditions. Now, when we really study the mechanism, we can figure out why this is the case. So let's take a look at our acetal and see what happens here. We may run out of board space, but we will see. So what's our end goal? We want to get rid of these two alcohol or these OR groups. So we're under acidic conditions, right? So when you have acid and water together, what will you generate? You'll generate the hydronium ion. And we see we have electron-rich oxygen, so that's going to come in. And this is all reversible. Now, why is this so important? Adding that hydrogen there because it makes it a positive charge, and now it is a good leaving group. So we can take these lone pairs on the other oxygen to help kick this guy off. So now we have a double bonded OR positive, and then we just kicked off the ROH. So there's our first one that has been kicked off. Let's see here. So we just, from this step right here, we have what? We generated water. So we can also see a resonance structure here that this carbon right here is going to be electron poor. So if we draw a resonance structure, do we see that resonance structure? So now we have a carbon that is electron poor, so the water is going to then come in and attack. And so that is reversible. So that's going to give us what? OR, OH, H. Positively charged. Let's see. There's no oxygen hydrogens with hydrogen, so we also have to get rid of these hydrogens eventually as well. So we have what? A lot of water hanging around. So that's going to be our base that will come in and abstract one of those protons. That will give us OR, OH, plus our hydronium. Okay, what is that species called that we just made? Your book calls it a hemiacetal, but I call it a hemiketal. Perfect. So that's one of the major intermediates here. But now we have to continue on with the mechanism. And so we have run out of board space So I am going to have to erase some things. So let's erase this top part so we can keep the mechanism. So we generated a hydronium right here, right? So can you envision, hey, we want to get rid of this one, so let's get rid of it by converting it into a good leaving group. And so this one is going to come up here, and this is all reversible. So we have now generated OROH. And we also generated water again. So now we have a good leaving group. So you can envision that these lone pairs on this oxygen is going to help kick that off. Now we have double bonded O, positive charge. We just kicked off the alcohol, so we have the second one. Now that, do you see how close we are to our product? What do we have to do next? We got to get rid of that oxygen. So we have water here, which is a base. And that is going to give us our product. And there is our ketone. Pretty slick. So I'm not going to go over these hydrolysis mechanisms with you, but you should be able to do them. It is the hydrolysis of imines and enamines. Let me write it out to show you what I'm talking about. If you have right there your imine, and then let's say you have your enamine. I'm the world's worst speller. Enamine. What you can do, we're going to hydrolyze amines and enamines. So that means we want to sever that bond. And the way we're going to do that is we're going to add some acid and lots of water. And what's going to happen there? It's going to replace it with our carbonyl. Because remember, it was the ketone plus the primary amine to give us the imine. But now we're just going in the reverse direction. So that's going to give us our primary amine, which was NH2R. So in this plus this will give us the amine, but then we can hydrolyze the amine back into our ketone. So know the mechanism. It is exactly the opposite mechanism of this forward process, of these two going to that. How do we hydrolyze the enamine? Same thing. You add some acid and some water. And that is going to give us back our ketone. But this, in order to get an enamine, we would have had to use a secondary amine, which would be that guy. So I'm not going to show you the mechanism, but I technically already did. I just did it in this direction. Now you just go in the opposite direction to do the hydrolysis. So the next nucleophile that we're going to look at is sulfur-containing species. So if we have a HSR, something like that, that is a sulfur-containing species, and we call those sulfide or thio. Not bad. We're going to start looking at our sulfur species, and they are also called thiols. So I typically will use the word thiol and sulfur containing species interchangeably. They're going to mean the same thing, okay? So what would the product be when you have this reaction here? And let's say we have excess of that. You're going to generate what? What's that? The ketal? Now, think in your mind, what was the mechanism to get there? But look at this. What if I take the same starting material and then just replace this oxygen right here with a sulfur? And that is our thiol. Add a little bit of acid. What are we going to get? Do you see that? Now your book, like I've been saying this whole time, it clumps together ketals and acetals together. So your textbook is going to call this compound a thioacetal. If you called it a thioketal, that'd be more correct. That's what your textbook calls it. So mechanistically, how do you go from the ketone to the thioacetal? The exact same mechanism that you use for this guy. So there's no need for me to show you. It's just you've taken this oxygen and replaced it with a sulfur. Same exact mechanism. So what if I did something like this? What if I changed the look of the alcohol to this? What would our product be? All right. So can you envision what I'm going to do next? What do you think the product's going to be? There we go. There we have, we would call that a cyclic. There's our cyclic thioacetal. Pretty straightforward. What's the mechanism for this reaction in green? The same one as in blue. Just you're replacing the O's with the sulfur. Now the cool thing about cyclic thioesters is it can do a reaction in which if you treat the thioacetal and you treat it with rainy nickel, it's going to reduce those bonds right here and turn our product into a simple alkane. So there's another way to make alkanes. You can start with ketones, convert it to a thioester or thioacetal, then reduce it with rainy nickel, and you get a alkane. Remember, just a few moments ago, we talked about how could we get this into an alkane? Well, we said the Wolff-Kishner reduction. Well, you can also use the cyclic thioacetals. So now let's talk about another nucleophile. Let's talk about hydrogen nucleophiles. Recall from previous chapters, when you take a ketone or an aldehyde and treat it with lithium aluminum hydride, you reduce it into an alcohol. And when you use lithium aluminum hydride, you're going to have to do it in 2 steps, the reduction and then the acidic workup. Now, this reaction has to be done under basic conditions. Lithium aluminum hydride is basic, and it's also nucleophilic. What's happening here is you see this carbon right here? There's 0 hydrogens. Then there's a hydrogen right here. Well, where did that hydrogen come from? That hydrogen came from one of the hydrogens on the lithium aluminum hydride. And I'm going to show you mechanistically how that happens. You can also take an aldehyde or a ketone, treat it with sodium borohydride in 1 step, and form the alcohol. So we see 0 hydrogens there and a hydrogen there. Where did that hydrogen come from? It came from one of the ones on sodium borohydride. So what I want to show you next is the mechanism using lithium aluminum hydride. Now the mechanism that I'm going to show you for this one is very similar to the sodium borohydride. So if we have our ketone or aldehyde, and if I draw out lithium aluminum hydride, I could draw it like this. And it's negatively charged, right? And so that makes this hydrogen right here, that bond right there, very nucleophilic. So that bond is going to come and attack like that and going to give us, I'll draw it like this. Negatively charged, and then we added our hydrogen plus our aluminum with 3 hydrogens. And then what's going to happen next? Well, we have the second step where it is a simple aqueous workup. And then that's going to go into our product. Now, when you practice doing the mechanism with sodium borohydride, the proton source is from the methanol. In the lithium aluminum hydride, the proton source that puts the hydrogen on this oxygen atom, so this one. So if we circle that, this hydrogen came from one of the hydrogens on the water. And then this one right there, when we used the sodium borohydride, came from that guy. So if you use the lithium aluminum hydride mechanism, it will guide you in knowing how to do the sodium borohydride. Another word of caution that you need to be aware of is that when you use lithium aluminum hydride or sodium borohydride, and you have a molecule, so let's take a different look here. Let's change this molecule up a bit up top. What if I added a carbon here? Just like that. And I do lithium aluminum hydride. What would our product be? It'd be that guy, right? But what did we also generate? We generated a stereocenter. So because this carbon is sp2 hybridized, this lithium aluminum hydride can approach from the front face and attack, or it can come in from behind and attack. So what's going to happen is if it attacked from the front face, you get a wedge. No. If the hydrogen attacked from the back face, we'd get a wedged oxygen. And if it attacked from the front face, then we would have a dashed alcohol. So you got to pay very close attention when you reduce an aldehyde or a ketone. Are you going to generate stereocenters or not? Very, very important to see that. So we have what? In this reaction right here, we're going to have a racemic mixture. Now I want to make this point. I think I've made it before. Your textbook calls these chiral centers. That's technically not correct because the center is not chiral. The molecule is chiral. So don't say chiral centers. Say stereocenters. That's the more accurate way of describing those carbons right there. They're stereocenters. How much time do we have left? We've got 2 minutes, so I'll introduce the next nucleophile that we want to talk about is carbon nucleophiles. And these are one of the most important because what we're doing is we are forming carbon-carbon bonds. We're expanding the carbon network. And that's oftentimes difficult in organic chemistry. Nature, animals, plants, they can form carbon-carbon bonds like gangbusters, like it's just not a problem to them. But when we go to the lab and try to form carbon-carbon bonds, it is a struggle at times. And so these next reactions that I'm going to share with you, they form carbon-carbon bonds, and so I'm hoping that you can come to appreciate them. Whenever you can form carbon-carbon bonds, that's a big deal. So the first one that we're going to look at is treating a ketone or an aldehyde with the Grignard reagent, and that will form ourselves a carbon-carbon bond. So time-wise, where are we at? 49 minutes? Okay, so that's where we'll stop. We'll pick up carbon nucleophiles in the next video.